Welcome back to the organic chemistry chapters. We're going to be looking at the oxidation of alcohols today, and I thought no slides, we'll just jump right into it. I did kind of write out a few things because it is hard to keep all this in your head, but yeah, let's get into it. So when we oxidize an alcohol, that means we need to make the oxidation state of that carbon attached to the alcohol more positive. So we can do that through oxidative reagents, or oxidizing agents, I should say. We can do this with primary and secondary alcohols. We can't do it with tertiary. We'll see why in a second. Okay, so to oxidize an alcohol, we can do an oxidation step with reagents we'll see in a second, and we can make an aldehyde right here. If we have an aldehyde, we could do another oxidation step and get a carboxylic acid, and this is for primary alcohols. So you can oxidize it twice. With a secondary alcohol, you can only oxidize it once, and you can oxidize it into a ketone with the reagents we'll see. And we'll notice that if you have tertiary alcohol, you will not get any reaction to occur there that will oxidize it into a ketone, because if we were to hypothetically put it on a carbon, this is so cursed. That would never work. This carbon has a filled octet by 2 electrons, and we know that will never happen. So yeah, tertiary alcohols, no bueno. So we'll draw a little sad face. We can't really oxidize those. All right, so for the reagents that can do these oxidizing steps, you have a couple. We have hydrochromic acid. That's this reagent here. And we don't just have it in the lab. You need to make it in situ, which means make it in the reaction vesicle itself. So you can do that through these reagents here. Na2Cr2O7 with sulfuric acid, or CrO3 and sulfuric acid. So either of these will give you this in situ. Quite simple. Our next reagent is called PCC, pyridium chlorochromate. You can see it here, this and this. It will do oxidation as well. Now the difference is when we compare the two, the chromic acid and the PCC, we need to take into consider the strengths. This is what we consider a stronger oxidizing agent, while this is kind of weak. So what do I mean by that? Well, if we come back up here, you can see this compound here, our primary alcohol. If we used PCC here, the PCC reagents, we'd achieve this reaction to get an aldehyde. But if we used PCC on the aldehyde, we would not get this product here, the carboxylic acid. We would not get this. And that's just because it's a weaker oxidizing agent. However, if we used chromic acid, so if we have our H2CrO4, we'll get the aldehyde, and then if we use another, we'll get another one, another oxidizing step, and we'll get a carboxylic acid. We're also going to investigate another reagent at the end of this chapter, or at the end of this video, I should say. It reacts much like PCC. It's called the Swern reagent, and it's this big jumbled mess here. I won't go through all of it yet, but we'll see it at the end of the video. It's a more green way, a greener reagent. Something important to note is that PCC is not good for the environment, neither is our chromic acid, and because of that, we came up with the Swern reagent, which does Swern oxidation, which we'll see later. Okay, so we have quite a few mechanisms, and I don't know how long this video is going to be. I hope not too terribly long, but I can already see it's going to be a long video. So we're going to start with the easiest of the mechanisms, which is the secondary alcohol into the ketone. So it starts like this. So our oxygen comes out to the chromium, and it's going to kick electrons onto this oxygen. A proton is going to be given by H2SO4. So I'll just draw H plus, and this oxygen will grab a hydrogen. So just in case we didn't see that there and I went a little too fast, oxygen of the alcohol that we're trying to oxidize of this compound here is going to reach out to the chromium center, pushes electrons onto one of the double bonded oxygens, and then some of those lone pairs grabs a proton from H2SO4. So we're going to get this here, and that gives oxygen a positive formal charge, chromium, and then you have quite the molecule here, I should say, and we'll just draw it all there. Okie dokie, now water comes in, and we'll say water. And it's just going to deprotonate, right? Because we have our acid, it needs to be done in water. So we reach out to the hydrogen, dump electrons onto the oxygen. And we're left with this here, with a lot of hydroxyl groups coming off. Holy crap. Quite a bit. Okay, now the next step is a little strange, but hopefully it makes sense. What's implied here is that there's a hydrogen, right? We don't draw it out because it's a skeletal structure, but it's there, and it's going to do something weird, of course, because it's chemistry, and why wouldn't it do something weird? Basically, it comes out here, and if we have our conjugate base of our strong acid that we used back in the first step to protonate our chromate, it's going to come back with its nice little negative charge, and it's going to eliminate it towards the oxygen, and it's going to kick off this. So this reagent here gets reduced, and our carbon here is getting oxidized. So that's a secondary alcohol into a ketone, and that's the product we get, and that's it. On to primaries. Okay, so our mechanism here for a primary alcohol, just write that here, a primary alcohol, is going to be kind of similar for the first step when we turn it into aldehydes. But we're going to see the next step when you use just your chromic acid and not PCC, that's going to make a carboxylic acid. So we'll show both of those little steps there. It's much the same, so I'll just draw lines as lone pairs to save some time. This here happens, same kind of step. This comes out to the oxygen that the pi bond gets given to the oxygen to make room, and lone pairs makes it protonated, so we neutralize the negative charge. Same exact thing. Alrighty, and this here. And we have that big goofy reagent on our molecule now. So 3 hydroxyl groups go on. Alrighty. Now water comes in. And we're first going to get this here. We could do the deprotonation or the elimination first. Doesn't matter. Comes in like this. Going to eliminate and kick off our leaving group. And that leaves us with this. Or sorry, not that. Well, there is an H there, but yeah, like this. Okay, awesome. We still have that positive charge, so how do we neutralize it? Well, we can come back and neutralize our conjugate base by coming in like this, giving electrons to the oxygen. Geez, I need to learn how to draw arrows. And we will get an aldehyde. All right, so now we have to turn this into a carboxylic acid. Okay, so now that we have our aldehyde, we're going to start this little reaction here with water. Now we need to do we need to make a hydrate. So what we're going to do is this ketone is going to get protonated by the water. And that puts a positive charge here. Now through resonance, we know that this carbon here is feeling a little more positive than the other ones. So we have a slight partial positive buildup there. So what happens? Hydroxide comes in. It's going to kick up those electrons, and we're going to form a hydrate. And we'll just draw it like this. Alrighty, so now that we have that, we're ready for that chromium complex to come in, or our acid, I should say. Alright, now it doesn't matter which alcohol does it, it's just one of them. It attacks this here. Now we're starting to see a very familiar reaction. Remember, that gets protonated, and we're going to have our H2SO4 come in here, pick up a proton to neutralize the negative charge that would form and give us the conjugate base. Quite simple. And I hate drawing this chromate reagent a million times, guys. It's really killing me, I'm telling you. Holy crap, there we go. Okay, now again, deprotonation or whatever works fine. So let's do elimination first, why don't we? So we'll come in with an equivalent of water. And let's just make it do that attack there. So it's going to steal that, do that, and kick out our chromium reagent. And we're left with this. So I will draw it like that with our hydrogen and our positive charge on there. And if we want to neutralize a positive charge like this, yeah, it's pretty obvious here. We can use some sort of basic species to get rid of this proton to neutralize the positive charge there. So in this example, because we didn't reform our acid, I'll just reform the acid. Pretty simple. So that gets a negative charge, it steals that hydrogen, and it's given to that. So we're left with our final product, a carboxylic acid. So those were all the steps there. We went from a primary alcohol to an aldehyde, and then we went from an aldehyde all the way to our final product here. Now I want to get into how PCC works. Alright, so now we have a little bit of a trickier mechanism to kind of remember. It's the PCC primary alcohol to aldehyde mechanism. Again, this will also turn your secondary alcohols into, you guessed it, ketones. So how does this reagent work? Well, let's look at the mechanism here. It starts off quite simple. We start off with, now this is an ionic species. That oxygen has a negative charge. Our base here has a positive charge. So ionic species. Basically, this will reach out here to the chromium, and it's not going to kick electrons onto this one because then the oxygen would break off. It's going to make a double negative charge, and that's pretty much a crime, and it's kind of is, but we'll see why that's okay in just a second. And we'll draw oxygen negative charge, double bond O, and we'll draw our chlorine. Okay, moving on. This is where our base comes in handy. So we have our base, And that goes like as such. Positive charge. One of these oxygens reaches out, steals the hydrogen. So we can neutralize a negative charge. Remember, here we have a positive charge. Forgot to draw that in. We have 3 bonds to oxygen. That's positive. And then we're going to get this here. Oh, guys, I'm gonna lose my mind if I have to draw another one of these reagents. I know I am. There's another step. Okay, so the next step of our mechanism is a little bit of, oh no! I forgot. We just protonated that. How could I forget that? Alright, so we have a negative charge there. We can neutralize it, or not neutralize it, but give it to another species who's more electronegative, chlorine, by kicking it off. So that's exactly what happens. Oxygen is electronegative, but chlorine is more electronegative. It's a halogen. So we lose a chlorine group, and we're left with a more stable compound. We're always moving towards more stability at the end of reactions, of course, hopefully. All right. So we have this here. And the next step of our mechanism, a lot of steps here, is we're going to do some elimination. So we'll use, let's say, we'll reuse our base, our pyridine base. Oh, wow, I made it look like a bird almost, a bird's beak over here. Jeez Louise. So this is ready to grab a proton. Let's just say it does elimination here. It's going to kick off the group here, reducing this, again, oxidizing our carbon here. So we get this here. And we still have that hydrogen bound, and that is simply some sort of base coming in and stealing that proton. So I'll just write base. Could be water, could be our pyridine here. Doesn't matter. Picks up the hydrogen, dumps it onto here, and we're left with an aldehyde. And if this was to be done under similar conditions to a secondary alcohol, you'd get the same product here. Just it would be a ketone. So quite simple. Okay, so if you don't want to use PCC, which has harmful chromium reagents, very toxic, not good for the environment, you can use the Swern reagents, which is a mixture of DMSO, oxalyl chloride, can never say that right, and triethyl ammonia. So I just drew this little graphic up here. If you love the earth, you're going to love green chemistry because this dude here is stabbing it to death. Any chromium reagent isn't really good for like fish. Like if that gets in the water with fish, it could probably kill them. So don't be the contributor to a bad thing. Use wonderful, nice reagents. So if we were to predict the products, we'd get the aldehyde here. Same. If we had a secondary alcohol, we'd get a ketone. So this mechanism can get a little complex, but stay with me here. So let's go over here. So we'll have to start our it's called dimethyl sulfoxide. So that looks like this, DMSO, right? And we want to look at the resonance factor, knowing that this is partially positive, this is partially negative. So for mechanism purposes, we'll draw it like this. So it would look like this, and this has a negative charge on it, and this has a positive charge. Alrighty, so now we have our big fat reagent here. We'll look back once more. The oxalyl chloride, and that looks like this, right? So it's a chlorine, carbon, carbon, chlorine, double bonded oxygens. And as you might guess, if anything's going to do nucleophilic attack on it, it's probably going to be this oxygen here with a negative charge, and that is exactly what happens, and I'll use a different color here. It attacks here and will pop up some electrons onto that oxygen. So when we draw our compound here, we have this here, and then chlorine, oxygen, chlorine, and we have oxygen now with a negative charge, and this oxygen's neutral. All right, so then we get some arrow pushing to emit a carbon, or sorry, a chlorine, not a carbon. Wow, that would be really nice if we could have nice ways of emitting carbons. 'Tis in our dreams, though, we say. Okay. So now we have this intermediate. Not a double bond there. We have this intermediate, and if the chlorine's close enough, there's probably going to be some reaction with it, and forgot to draw in, there's still a positive charge here. Just wasn't important in those steps. But now it is important because it's part of the reaction. So chlorine, being a nucleophile, is going to attack that electron-weak sulfur atom, and it kicks out this group. But we're going to get some side products here. So we we break this sigma bond here, giving this a negative charge, but then some electrons fold in to make carbon dioxide in a way, and because of that, it's going to detach here, and we're going to see that this oxygen here is going to make a triple bond and kick off the chlorine. So there's a lot of arrow pushing, but just know that we're going to remove CO2. We're going to remove carbon monoxide, and we're going to yeet a carbon out of there too. So those are some important waste products that get formed. These will most likely, under standard conditions, be a gas, so they'll bubble out of solution. Now, you might be saying, oh, carbon dioxide, carbon monoxide, not good for the environment. And you'd be right. Contributing to the CO2 crisis does cause global warming. No bueno. But it's way better than using those toxic chromium reagents. Okay, so let's now draw our active compound, as we call it. And it will look something like this. All right, so this part of the mechanism is quite short. We have our nucleophile, our electrophile, the chlorosulfonium. So the oxygen attacks that electrophile and attaches as such. And an important note is that chlorine will get kicked off. Oopsies, forgot that step. I'm just a boy. Alrighty, and we'll lose that hydrogen through deprotonation through the base here, but I don't really care about writing that out. I'm sure you can write a deprotonation step. It's nothing spectacular. Okie dokie. So the next step here is that we're going to get a deprotonation step. So one of the hydrogens, but it's not going to be here like we've seen. It's going to be here on our sulfonium ion. So our base comes in once again, and that should be a 3. It's going to take that, and we're going to just draw the resonant form where the negative charge is put onto this carbon here. So quite simple. And we will put the negative charge right on that carbon. So here's where we see maybe something a little familiar, like our other reactions. So that negative charge, we're going to see some sort of intramolecular process. It's initiated by that negative charge reaching out to this hydrogen. This hydrogen eliminates itself to make a C double bond O, and then this breaks off as such. So we're then left with, in this case, an aldehyde. If we did this with a secondary alcohol, we'd get a ketone. Okay, so one final reagent that we can use that's very helpful is called DMP, also known as Des-Martin pyridine. And we commonly do this in dichloromethane as our solvent, right? And it's much like what we've seen with PCC or the Swern reagents. It's going to make either an aldehyde for a primary alcohol, or for a secondary alcohol make a ketone. This is what the reagent looks like. Big, complex, nice looking molecule. Has an iodine in there, pretty interesting. And some benefits here is it's going to keep your reaction conditions mild. You don't have to tweak any high heats, high pressures, anything like that. And the shelf life of this stuff is better than the other reagents we've seen, so always a plus. Although I believe this stuff is quite expensive, so that's the one downside. It's also green too. It's a nice green reagent, less toxic than our chromium reagents that we've seen. And I didn't feel like torturing you guys with awkward silence, so I just drew out the mechanism here. It's quite simple, so I'll just describe it here. You're probably not on the hook for knowing this one, but our oxygen reaches out to this iodine here and kicks off this group here. This group here and this group here are equivalent, and I believe it's called an acetone oxy group that we're emitting, and that's what we lose here. This hydrogen will be deprotonated by some means, and we're left with this intermediate here. We get an interesting little rearrangement. It starts with one of those little acetone ester groups coming out, and first of all, we're going to see that this double bond grabs a hydrogen. Then that bond between hydrogen and carbon breaks to form a double bond here. And then we can see here that that sigma bond breaks and gives iodine some electrons. And then this bond breaks here to make another one of these groups here that leaves. So I should actually write here minus your acetone oxy group. I'll call it that. I doubt it's called that, but acetoxy, something I forget. I'm close. And then you get your final product here. It's actually not that bad of a mechanism. It's just remembering this fat reagent here is kind of a pain in the butt. But the chances that you need to know the mechanism for this is quite low. So, yeah. Wow, that was a lot of mechanisms. It's all over now. That was about 27 minutes of pure organic chemistry, so I'm sure your brain is a little fried. But don't be scared, because I don't believe you'll need to know all the mechanisms. You just need to know that the reagents that you use will get you to your products. That's quite important there. I doubt you'll need to know the Des-Martin pyridine mechanism. You might need to know Swern. You might need to know just your basic chromic acid reagents and mechanism. But you definitely need to know that, or PCC I should say, but you do need to know that which reagents do what, and knowing the mechanism can help you keep that in your head. So have a wonderful day, guys.